Okay, so inductance.
We need 3 times.
And inductors. So we talked about capacitance and capacitor. You can ask the question how much the device is called the capacitor. The device here is the inductor. And the other device is the resistor. Resistor has resistance, inductor has inductance, and capacitor has capacitance, right? Okay. And the symbol for an inductor we mentioned, it looks like this. The wire itself is a conductor. It's conductor, so it doesn't have any, you can assume it's a perfect conductor, so no resistance at all. Okay? The reason for the potential, so we mentioned this. If the direction of the current is this way, then the potential difference across the inductor from here to here is delta V inductor, and it is equal to minus L di dt, right? We mentioned this. Okay. And we talked about self-inductance last time. In the worksheet, I talked also about mutual inductance. And I think we talked about the energy in the inductor also. The energy in an inductor was 1/2 the inductance times the current in the inductor squared, right? That's the energy in the inductor. And we also talked about the energy per unit of volume. And we said that was 1/2 u0, and then the magnetic field squared. And now we would like to put an inductor in a circuit, and see what happens, what we get. Okay? Okay, we want to see the behavior of an inductor. So, inductor circuits. The first one will be this. We would just have a battery, here's the switch. We have a resistor, and then we would have an inductor. And this is your battery, right? This is your resistor. Okay. I will do this only one time, but from now on, we will just use this rule. Okay, here's what I'm going to do. Let's apply, I'm going to close the switch and ask what happens, right? So, according to Faraday's law, so let's close the switch. As you close the switch, in what direction will the current flow? It will, the positives will start going clockwise. So Faraday's law says the integral of E dot dl or E dot ds is equal to minus d phi dt, right? The time derivative of the flux. And the time derivative of the flux is L di dt. Because remember, maybe I should write it here. The flux, the inductance was defined as the flux over time, right? That was the definition of inductance. So the flux would be Li. So minus d flux dt. So let's do it maybe. That's equal to minus d flux dt. So it's minus d dt of L times I. And so you got the integral of E dot ds will equal to minus L di dt. Okay? That's Faraday's law. I'm going to multiply both sides by -1 for a reason that you will see in a second. Multiply by -1. We get E dot ds is equal to L di dt. Okay? L di dt. Now what is E dot ds? The minus integral of E dot ds. It's the voltage, yeah, the potential difference. The potential difference around the circuit. So, from here to here, what's the potential difference? V. And then if we're saying the current is going like this, and so that's V. Let's see how we. So this whole integral with the minus sign is the potential difference. So you got V, and then minus IR, right? Minus IR equals to L di dt. Move the L di dt to this side, and I just want to show you just one time. L di dt equals to 0. So here's the rule that we're going to go by. If you go in the direction of the current, so the voltage of the battery is V. In the direction of the current, the voltage across the resistor drops by an IR, right? This is from basic circuits chapter. Now, the voltage across, if you jump the inductor in the direction of the current, the potential change is this minus L di dt. So from now on, we'll just use this. No reason to go back all the way to here. Okay? Mathematically, it's the same. Okay, so now the question becomes, how do we solve this equation? How do we solve this equation? The first thing we need to realize is that the initial current has to be 0. The initial current has to be 0 initially. Okay. So you close this, when you close the switch, the question is how much current would there be? The answer is it has to be 0. Does anybody know why? Okay, yeah. So what happens is, I like that. So I think what you're saying, there would be a magnetic field. If you're saying there is a current, and let's say it went from 0 to something instantaneously, it means there is a magnetic field. It means there is energy. And so the energy went from 0 to something. From 0 to something in no time, that's an infinite amount of power. Because power is the change in energy over time. The other way to think about it is, if the current jumps from 0 to something when you close the switch, let's say from 0 to, I don't know, some number. So the current will go from 0 to some number, right? That's a step, and that's an infinite derivative. The I dt will be infinite. So the potential difference has to be infinite. Do we have anything that's providing us with an infinite potential difference? There isn't. So long story short, the current has to start from 0 and then grow when you have an inductor. So what it does, when you try to run a current, what do inductors do? They oppose you. They oppose you. They always do the opposite. So they will oppose that current change by inducing their own EMF to oppose it. So initially it will start to 0 and then relaxes and eases. So let's solve this equation here. It's a differential equation, so we will we'll do this. Let's solve for di dt first. So you get di dt, we move it to the other side, so you get di dt, and divide everything by L. So you get v over L minus R over L I. Right? If you move it to the other side, this one, V minus IL, V minus IR stay here, divided by L. So you get that. Now, that's an equation that we have to solve. How do we solve it? You can say, well, guess the solution, but here is one way to do it, very similar to the capacitor. Very similar to the capacitor. So here is one way. It's, of course, not the only way. You can just directly integrate it also. But I think this might be easier. So let this number, this symbol here, x, just a new variable, x, equal to v over L minus R over L I. So define x to be there. V over L minus I minus R over L minus I. Okay? Then take the derivative of x. So dx dt. I'm just changing this variable to make it easier to solve. It would be easier. So if you take derivative, v over L is a constant. Its derivative will be 0. So you just get minus R over L di dt. That means the IDT will be, solved for the IDT, it will be minus L over R times dx dt. Now substitute everything in this equation. So this equation therefore becomes what is the IDT now in terms of x? Minus L over R dx dt. Okay. So it's minus L over R dx dt. That's one thing. Equals, on the right hand side, what did we decide to call V over L minus R over L times I? X, right? That is just x. So x, and therefore dx dt will be minus R over L times x, right? Now this derivative of something equals to itself times a constant is the exponential function. So the solution would be x would be some number, some constant a, which we'll determine in a second, times e to the minus r over n times t. That's the solution. And now we'll go back to our original variable. We'll go back to our original variable. So I'm going to replace x by this. I'm going to go back to my initial symbols. So I'm going to go to this equation, but replace x. So here it is. On the right hand side, I have a e to the minus r over l times t. On the left side, I have x. But x is this v over l minus r over l times the current. Okay. So now let's use our initial condition. What did we say? At t equal to 0, what's the current?
0.
Okay. So at t equal to 0, we have I has to be 0. So at t, plug in 0 for t. So the current is 0, so you get v over L equals to, what is e to the 0? 1, so you just have a, right? So this symbol a is v over L. This constant a is v over L. So let's now, so we have this v over L minus r over L is equal to, instead of a, I have v over L e minus r over L times t. Multiply everything by L, so L goes away. And solve for, oh, did I forget the I here? R over L times I, right? I left out the I, so there is an I here. I want to solve for I. So, let's see. So I got, move this to this side and this one to that side, so I get V minus V e to the minus R over L times t is equal to R Ri. Divide everything by R and factor the V, so you get I would be V over R times 1 minus e to the minus R over L. That's the current as a function of time.
How did you get x equals to a minus r negative r?
This is the differential equation, and that's the solution to it. So
Okay.
the function whose derivative is equal to the function itself times some constant is the exponential. So that's V, I'm sorry, current as a function of time. Let's plot the current as a function of time. So you got, here's T, here's I, starts at 0, and then, so at t equal to 0 is 0, at t equal to infinity, when t goes to infinity, e to the minus infinity is 0, and you just get v over r. So you get v over r here. So the current will go like that. Okay. So this, what this means is this. Initially, the inductor behaves like a capacitor when it's fully charged. Remember, when the capacitor gets fully charged, it doesn't allow any current to pass by. But initially, when the capacitor is not charged, the current will go through as if it didn't even exist. So the inductor is like the mirror image. An inductor at t equal to 0 is like a capacitor at t equal to infinity. And an inductor at t equal to infinity is like a capacitor at t equal to 0.
Yeah. So, it's opposite of capacitor.
Opposite of capacitor, the behavior, yeah. So basically, the inductor is like a resistance, no resistance conductor, right? So after a long time, when the current is no longer changing, it's just a wire, and it doesn't even exist. And the circuit behaves like you just have the battery and the resistor after a long time. But initially, it will not allow any current through. The capacitor, on the other hand, is different, is the opposite. Initially, before the capacitor is charged, the current will just flow as if the capacitor is not even there. But when the capacitor gets fully charged, it will oppose the flow of current, and then it's like a broken circuit. It doesn't allow any current to go through. So they're just mirrors to each other. Yeah.
So the job of the inductor is kind of to slowly increase your current.
That's one of the, yeah. We will have, it has other things that it can do, yeah.
So,
Yeah.
just to return, so when there's no charge in the inductor, it doesn't allow any current to pass.
When there is no current, yeah, initially.
Or when there's no current,
Yeah.
it doesn't allow any current.
Any current at t equal to 0, yeah. So that's the inductor. Now what if the inductor now, not discharged, but let's say there is current already flowing in the inductor, but now I change the circuit a little bit. So here's what I'm going to do. Suppose now I'm going to go to that circuit again, and I'm going to draw it right here. So here is the battery. Here is the switch, or actually the switch is now closed. Here is your resistor, and here is your inductor, and here is V, right? R and L, right? So now there is an established current this way. There is current, in particular, the current is going like this. There is current. And everything is okay. So there is current, it's V equal to IR. Yeah.
Why is that? It should be L, right? Not R?
L. Thank you. Yeah. Good. So now there is a current, everything is happy, everything is good, right? Here's a question. If I put a resistor here, another R, what would the current through this resistor be? With any current flow.
Same as well.
Be all of it.
It has to be
That
with-
way at t equals 0 or just.
Oh, good. So at t equal to 0, yeah, all of it will flow this way because the inductor will not allow any. But at t equal to infinity, will any current flow through this?
No.
No, because at t equal to infinity, the conductor is like, the inductor is just like a wire. It's a shorted circuit. So all the current will flow this way. All the current will flow this way. Because basically, V minus IR, well, I is equal to V, IR is equal to V, so V minus IR is 0, and so that's it. You cannot have any current this way. All right, so now here is the question. Let's say, so let's go back. So we have a current already flowing, right? We agree with that. The current is flowing. Let's open the circuit now. What happens now?
Nothing.
Oh,
So the current wants to flow, but there is a gap.
goes the other way?
It will go this way. It will have, you see, you have current this way. Now, it wants to go this way, but now there is a gap. So there is an infinite resistance here, right? There's a gap, means the resistance is basically infinite. So it will go this way. And the question is now, what is the function? What is the behavior here? So let's go with it. So here's, the current will go in this direction, this way, and then around, right? So let's do this one, RL, just the R and the L. So in other words, here's what we have. You have an inductor, you have a resistor, and the current is going like this. R and L. The question is, what's the current? Will the current run for ever, it will stay constant, will it die out, what happens?
It'll die out.
It has to, yeah. Any current that runs through the resistor, that's I squared R of power, and so it's, the resistor will lose energy, and you can't have the current to be the same, right? Every time you lose energy, the current has to decrease. So let's do that. So again, we cross an L, so what do we say about the potential this way? By how much will it change?
Negative L D A D T.
Yes, so minus L di dt, minus L di dt. I'm referring to this. In the direction of the current, the potential changes with it. And that's back to Faraday's law. But for now, let's just do it this rule. If you're going in the direction of the current, the potential difference is this. Okay? So that's that. And then we're going in the direction of the current. Current flows from low potential to high potential. So, I'm sorry, from high potential to low potential. So the change here is minus IR. So minus IR equals to 0. And that means move this to the other side and divide. So you got di dt minus R over L times R. And again, derivative of something equals to itself times a constant, that's the exponential. So I equal to the initial term e to the minus L over L times the y. This is called just the initial term. The current that was in the inductor at t equal to 0. Right? So that's what happens. So the current will die out in this case. The current is t, here is I, here is I0. In principle, the current will take how much time for it to go to 0? Infinity. So basically, if you have a light bulb hooked to an inductor, in principle, you would have current in there forever. But you won't see anything pretty much after a few seconds because the current would be so low. Okay. Now, LC circuits. Okay. An inductor and a capacitor now. I want to do that. And that will wrap this chapter. LC. Here's what we're going to have. A capacitor, a switch, and an inductor. C and then L. Initially, the capacitor is charged. It has a charge Q0. That's the charge of the capacitor. All right. So what are we going to do? Leave the switch open? No, we want to close it. Okay. So otherwise, nothing interesting happens. So we need to close the switch. So let's close the switch. So remember, initially the charge is Q0. Close the switch. In what direction will the current flow?
Clockwise.
We'll go clockwise. Good. Clockwise. So let's do our loop rule. So across the capacitor, what's the change in potential? You go from minus to plus. Huh? What's the change? What's the potential difference across a capacitor?
Q
Q over what? Over C, yeah. It's Q over C, yeah. Yeah. So for the capacitor, you get Q over C. Not Q0. Q0 is initially, but at some point it's just Q. Whatever it is at that particular moment in time. Go around the inductor, you get minus L di dt, right? And we're done. We loop, get 0. Now, let's think about the relationship between Q and I. So first, what happens to the charge? Increase or decrease? Yeah, yeah. When charges flow, it starts to decrease. So that means the current is dq dt But since the current, that's the correct direction, you have to put a minus sign here, because dq dt would be negative. You put a minus sign on it, it will be positive, so that's the direction of the current, that's correct.
After a long time, that's just one.
We'll see. It's an interesting behavior, yeah. It would be some, well, we'll see. So that's the current, so di dt therefore will be what? Will be minus what? The second derivative, right? Of q with respect to t. Okay, so let's put it here. So you get q over c minus L times di dt, but what's di dt? It's minus dq dt. But there is a minus sign here, so it becomes what? Plus L, second derivative of q with respect to t equals to 0. Move this to the other side and divide by L, so you get the second derivative of q with respect to t would be minus 1 over LC times q. Now the second derivative of something equals to itself times a constant. What is that? It can be e to the something, it's possible, or sines and cosines. If you say e to the something, the problem is this minus sign. If e to the something it's a positive quantity, so plus times plus, it should be plus, but it's negative. If it's a negative quantity, minus times minus, you will get plus, but it is negative. We'll see. I mean, if you allow for complex numbers, e to the I something, then it can be this. But for now, it's sines and cosines. So it'll be a sine or a cosine. In fact, it will be a combination. You have to assume it's a sine plus a cosine. But in this case, it will just be the cosine. Because at t equal to 0, the charge was not 0. So we can say, here is q of t will just be q0 times the cosine of omega times t. And this omega is 1 over the square root of LC. Because when you take the derivative twice, what do you get? You get an omega squared out, right? And omega squared, if it's 1 over the square root of LC, you just get 1 over LC. So omega is 1 over the square root of LC. That's the natural frequency of this. So it will oscillate. What does this mean? Let's see how it goes. So the charge will be changing over time and oscillating. Sometimes this plate will be positive, sometimes it will be this plate that's positive. So let's see how that works. I'm going to draw it. It started like that, right? Initially. So it started like this. I need to come here. Starts here. At this moment, Q is equal to Q0, and the current is 0. The current is 0. Well, how do you know that the current is 0? Take the derivative of this and plug in 0. What's the derivative of cosine is sine, sine of 0 is 0. Current is 0. As expected, right? Initially, the inductor will oppose any flow. Later on, we have this. There is no charge here now. The capacitor is just neutral. Q is just 0, but the current is maximum. So there is a current now in the inductor. So the inductor will have a current. Okay? And that current, so you see you have all the pluses, they are flowing here. So now you have as many pluses as minuses here, so both are neutral. But as long as there is a current, it keeps adding pluses and taking away pluses from here. So in a little bit, this side will be the plus and this side will be the minus. And you cannot just get rid of this current right away. See, the inductor slows down things. It's like inertia or like mass. Because it does the opposite of what, once you get the current going, well, it will take some time to stop that current. Because if you try to slow it down, well, it wants to keep going for a little bit. So here is the next thing that happens. You would have your now capacitor. Here is plus, here is minus. And now no current here. So in this case, Q is equal to minus Q0. Q, I mean, the one on the top plate. And the current is 0. And then finally, for this one, we got your capacitor. Your inductor. So now, after you fully charge the capacitor, it's like you're starting from scratch. It's like you're starting here, but the current will flow this way. Because this is now this is the plus, this is the minus. So now the current will actually reverse direction. The current will go this way. There is no charge, so that in here, Q is equal to 0, but the current will be equal to I maximum. If you want to include the direction, you can put minus, because it's the other way. And finally, you get back to here. So each of them would take a quarter period. Yeah.
So I don't really understand how it goes to negative Q naught. Like, I would think it would be a little less than negative Q naught.
Why not? Or why? The math will tell us it's actually flat. It's a cosine, right?
Yeah.
And a cosine looks like
Yeah, but like, when you look at it,
Yeah.
like you think that the positive charges would, when you get to that neutral stage, your Q is 0, right? So how does it keep on pushing more positive charges?
because there is a current already established in the inductor.
Oh, it doesn't change.
It doesn't just stop right away, yeah.
Oh, okay.
Yeah, it does not stop right
Oh,
away.
I thought it opposes the,
It opposes the change, yeah, so now the current will, you would, as you put charges on the capacitor, it wants to oppose it, but it doesn't stop right away.
oh, so it keeps on opposing it
Yeah.
even though there's.
It's similar to, you may remember the spring mass system. Here is the 0, here is a spring. Let's say you stretch the spring and you place the mass here. 0 velocity, but the displacement is maximum, right? X is maximum. Later, what happens to the spring? It will go by the equilibrium point, right? This is the mass. It will go by the equilibrium, but here you will have maximum velocity, no, the position is 0. And then later it will overshoot and compress. You see, when it gets by here, it doesn't just stop because X is 0. It will continue, it will slow down until it gets to here, and then back to here, and so on, and repeats the cycle. Okay, yeah.
So this behavior just happens based off of our analysis of ELC circuit?
Yes.
And how like there's a double derivative of Q?
That's correct, yeah.
Okay.
If you put a resistor with them, then every time it will behave like that. The only thing is, if there is resistance,
They're dampening?
yes, there will be like damping. It will die out kind of exponentially. Yeah.
I just want to make sure I get it, like, can you just remind me like why the inductor opposes the current initially?
So, yeah, so if you run a current, what happens? You will have a magnetic field, right?
Yeah.
So you're trying to induce a magnetic field in a loop, so it will oppose you.
Okay.
Yeah, so, just from Faraday's law, basically.
Okay.
Yeah. So you have no flux, but now if you run a current, you will start to have flux going through, so there is change in the flux, and therefore it will oppose it.
Okay.
It will counter it with a current that runs it the other way and makes it just a total 0 current.
Okay.
But eventually, if the change, see, it opposes like the sudden change or any change, but slow enough, it will accept it basically. Okay. in accordance to this mathematical equation. I think I saw another hand. No? I do, but, there is one thing that I probably, let me spend a minute on it.
Professor,
Yeah.
can you put that board in up?
This board is up and this one down?
Yeah.
Yeah. So let me talk about transformers for a second. So I just wanted to mention a transformer and how it works. And I'm going to erase this board here. Anybody? And maybe even AC circuits for a little bit. So, assuming I have something. All right. So transformers. Here's a basic transformer. So here's a basic transformer, okay? So you have an AC source. An AC source means the voltage is changing with time, or the current flips direction with time. So how do you get an AC source? Remember the generator that we showed? And here's the symbol. For a DC source, you have a battery, right? For an AC source, it has this symbol, AC. So basically something changing over time, some sine or cosine function. An AC source is like the power that you get from the wall. So here's your AC source. Make some windings around this. And this is the voltage in this primary source called VP. The VP for primary. That's the primary source. P for what? Primary. Good. There are a number of loops here. So the number of loops are called the number of loops in the primary, NP. Now, let's say this is 220 or 120. I want to step it up and make it 220, or maybe I step it down and make it 50 or 70 or something. So here's how we do it. So you take your secondary coil and wrap it on top of it. So this is the secondary. And your secondary, you have a switch, and you have your some resistor here, your hair dryer, something, radio. So that's that. So this one is called the secondary. So it has NS, number of loops in the secondary is NS. There are two assumptions for an ideal transformer. The assumptions are there is no flux loss and there is no power loss. Meaning, the flux through one of the loops in the primary should equal to the flux through one of the loops in the secondary. This is the first assumption. In secondary, the power given off here has to equal to the power given off, taken by this one. Just by conservation of energy, we're assuming